Welcome to NFTeasy session 4, the only guild on the internet where I promise to speak about NFTs and then don't for most of the time. It's my favorite new thing. It's really wonderful. Thank you so much for your patience and your humor. It's been wonderful going through all of this with you. And we really have crossed, great and vast oceans. We have looked at the nature of Git and seen how it is the precursor for many of the most innovative solutions that you'll see in blockchains, from cryptographically linked commits to content addressability. We've taken a look at various different frameworks for developing in Ethereum, like Hardhat, which is the one that we landed on and have used since then. We've looked at the specific libraries that we needed, which mostly kind of came down to the Open Zeppelin libraries, and we'll be looking even more at them today because there's so many cool aspects in there that you can use for more creative kinds of code, more collaborative kinds of co-creation, one might call it. And we spent some time also considering all of our dependencies, looking at the problems of funding open source work by reading the poetry of cooperation as it unfolds in our terminal and tells us about all of these NPM packages which need auditing, or who the author is looking for a job or needs funding of some kind, and puts a Bitcoin address into your terminal. We actually paid attention to all of those stack traces. We then wrote our own contracts. We looked at what it meant to leverage the Open Zeppelin libraries via the inheritance that Solidity provides. And then last week, we kind of updated our contracts to prepare it for production by including some proxy addresses for OpenSea, which allows us to have a smoother user experience on their platform and ensure that people can sell and trade and buy NFTs without having to approve them. That required, some deep investigation on chain into how those proxies actually work, what Wyvern is, what a first order decentralized exchange is as opposed to zeroth order. We took a look also at the difference between Arweave and IPFS, and I made an argument for the interesting aspects of Arweave's approach to incentivization, particularly its notion of adaptive interacting incentive agents that allow for us to just simply pay once when we upload content and then be sure that it will be available as long as the weave is available, as opposed to IPFS, which has admittedly the coolest algorithm name in history, which is proof of spacetime, but which forces us to kind of pin our own content or pay somebody to do that for us, which is certainly interesting in different contexts, but perhaps not quite the sort of trade-off that we were willing to make in terms of trying to ensure that as many aspects of the stack are decentralized as possible without being completely idealistic about it. Now, the question arises today. We have this contract, it's ready for showtime, but how are we going to actually mint and distribute these NFTs? And so much of the conversation in the wider community at the moment is how these particular linguistic primitives can be used to create community and as vehicles for culture, right? That many of the projects engaged in this kind of work have cultural intent. And the question arises, as I say, how do we actually not just write the actual code and get amazing graphics or art or video or music or whatever it is associated with our non-fungible token? How do we get that to people? What are the different ways in which we can go about that? Because certainly if you're doing it on the Ethereum mainnet and say you want to mint 10,000 NFTs and it costs, depending on the gas prices at certain times, between $20 and $50 to mint an NFT, you're suddenly looking at 10,000 times $20, a lot of money in ETH just to mint your NFTs, if that's the method that you're going to take, which is certainly what our contracts have left us with, right? We have the ability, based on what we did last week, to either mint a single NFT or batch mint NFTs. But as I say, for any kind of large scale projects, that's going to get very expensive very, very quickly. And so we have to think about alternative distribution mechanisms that will allow us to engage with and create the kind of community that we're interested in building with these tools without having an upfront capital cost of like $200,000, right? Because ain't no artist got time for that. So there are a number of mechanisms that we're going to look at in the course of today for what we can do to mitigate these kind of upfront capital costs and potentially get people to mint their own NFTs. And if it's just one person minting an NFT, they can kind of absorb that particular gas cost. And in fact, there are some methods where people only need to mint the NFT to either prove ownership of it or to transfer it to someone else. You know, if you, the third method that we're going to look at today, the Merkle drop, means that all of the information about who gets to mint and own an NFT is already stored in the Merkle root. So technically speaking, you don't even really need to mint your NFT unless, as I say, you want to transfer it to somebody else or prove ownership of it. So there are these really, really interesting kind of ways of doing these things, which, as I had kind of mentioned in a previous guild session, relates to this really interesting way of minting NFTs, and indeed creating or instantiating contracts that you might never need to actually deploy in production. And that is done with the create2 opcode. And you can sort of take a look at some of those ways of handling anything from insurance to, as I say, proof of ownership or transferability in NFTs. So the three basic methods that we're going to look at today are having some kind of minter role in your contract who is able to specify which addresses are allowed to mint which NFTs. And there are two different, or in fact, three different ways of doing that. And then the alternative method, which is actually cheaper and the one that we will get to toward the ends of this session, and the one that we use at Kernel for the gratitude NFTs, is uploading a Merkle root into your contract. And we'll take a look at what that actually means, what a Merkle tree is, why it's a data structure that we might be interested in using when we get there. But for the first little part of this, we're going to have a look at this notion of buyer mints NFT in a fairly simplistic way, where instead of us like minting an NFT and specifying the account that it gets minted to, we have a minter role in the contract, and it specifies, okay, Alon 0x dead beef can mint token ID number 3 and submit some kind of cryptographic proof that means that when Alon signs a message from that account, which has been specified, then an NFT can be successfully minted. As I say, there are three different approaches to doing this. Angela is very happily going to walk us through the actual implementation of this, but I'll just give you a very broad level overview of what these approaches are and how they differ. The first is there is this notion of a signed message on chain. And so it works in exactly the same way as you would sign a transaction. If you look into, in particular, the Web3 library, this is quite obvious. Ethers has it slightly differently, where they'll say send transaction and sign message, but it's the same basic idea, where in exactly the same way that you use your private key to sign a transaction that you send onto the chain, you can sign any arbitrary data, in fact, which is what a transaction is. It's just data structured in a particular way to cause some kind of state changing function in the EVM, but you can sign any arbitrary data that you like on chain. And this is what signed messages allow you to do. But there are a few little gotchas in this, right? Like the signed message was included right when Ethereum began, because we knew that it would be an interesting feature to, have widely deployed public key cryptography and be able to sign any arbitrary message. But the way that that actually happens, and you might have seen this if you've developed anything, is that when you sign a message as opposed to a transaction, you have to include like some kind of string at the beginning of your signed message, which often begins like X19 Ethereum signed message or XN32 Ethereum signed message. And it's just like a weird little string at the beginning of signed messages that is there by convention, so that anybody who is processing that signed data know that this is a signed message rather than a transaction. And the reason that this is like not exactly the best way of doing things, particularly in the environment that exists now, is that there is no real context passed along with these signed messages. So I don't really know what contracts this is a signed message about, where it's sort of meant to go and what it's specifying. And I don't know like which domain it's operating in, i.e. on which chain is this signed message relevant for? Is it on Ethereum? Is it on Polygon? Is it on Rinkeby, Ropsten, POA? Is it on BSC? There's no sense of wider context, right? Which has become more and more important as more and more EVM-like chains have proliferated. And so as a response to that, one of the earlier EIPs that was created was something called EIP 712. So not 721, which is the NFT standard that we've been working with all of this time, but 712 is called signed typed data. And this has been through various different iterations. It's one of the most contested EIPs, in fact, in the whole canon. There are many different people with many different use cases who think many different things about the way in which data should be signed so that they can consume and display it to the user. But the two critical things to know about 712 is that it's a very general EIP, right? So there's actually three things to say. It's a very, very general EIP, and it doesn't like give you as many specifics as, for instance, 721 or ERC20 would. It's much more kind of a general set of guidelines. You know, you can tell that it was written by pirates and not by profiteers because it's all about guidelines rather than rules. And it has been through numerous different versions. The one that is used by MetaMask and therefore by most of the rest of the Ethereum ecosystem is version 4. And it has two critical things, right? The one is the notion of a domain separator. So you specify what chain this is happening on, whether it's the main nets, whether it's one of the test nets, whether it's POA, whether it's Matic, whether it's BSC, whatever. There's this notion of a domain separator. And then part of that domain separator is also like an address, some kind of contracts that this particular signed data has to do with, so that it's easy enough to identify what signed message relates to what contracts for wallets. And that's the second important part of this, which is that 712 has associated with it the notion of some data structure. So you have to specify like the domain in which you're operating, which is the chain, and the address of the contract, and then the data structure that this is a particular like a signed message for. So if I want to sign in to an account, then the data structure is very simple. But if I want to, for instance, in this case, create a minter role in an NFT contract that allows anybody to mint an NFT if they've been authorized by that minter, then my data structure is likely to be an address and a token ID, an address and an unsigned integer, probably of 256 bits. So you would specify those two things. And that allows, for instance, MetaMask, you would have probably seen this if you've been around for a while. Sometimes when you get asked to sign a message in MetaMask, it's pure gobbledygook. You know, it's not even just ASCII. It's like all sorts of random stuff comes up in your MetaMask and you're like, oh, like what the hell am I signing? Right? That's the first option. That's signed data, an ETH signed message, right? So there's nothing kind of fancy about it. And it's really bad from a UX perspective. Not only does it lack context about which domain it's operating in and what contract it applies to, the end user can't really see what it is they're signing because the wallet cannot consume and display that data in a clear and coherent sense. Whereas if you implement 712, the signed typed data in your contract, which we will show you, then whenever anybody is signing a message to do with your contracts, it's very, very clear what they're signing. And MetaMask will display it correctly and say, like, you're signing this message, which has to do with this particular data. And it's, you know, a much clearer user experience, which is much better for everybody involved. And if you can think about it from like the use case that we're talking about here, there is a notion of an artist, right, who would be the minter, they would have the minter role in an NFT contract that they deployed, and you would want them to be clear about what it is that they're signing as they enable more and more people to mint NFTs in their contracts. The third and final method is another confusing number. It has come about slightly more recently. It's called ERC 1271. So with the 7s, the 2s, and the 1s. 721 is the NFT, 712 is signed type data, and 1271 is like smart signed type data. And what that means is that it's very, very similar to 712, where it has this notion of a domain separator and a data structure, but it decouples the signer from the identity. Because in many of the more modern wallets, like Argent, or I think Rainbow is kind of like this sometimes, certainly Argent, Gnosis Safe, and a few others, where you have a smart wallet, i.e. a wallet that is a contract. So, Gnosis Safe has these multi-sig wallets, which are contracts. And then your signer and your identity are not necessarily the same person, right? And 712 assumes that they are. And so if your contract only implements 712 as like a signed data type, then people who are using multi-sig wallets or a smart wallet from Argent or one of these social recovery schemes, really they struggle to use it. In fact, they can't, because it's the notion of signer and identity are tightly coupled. They're one and the same thing. Whereas with 1271, they're separated. And so you can have exactly the same, like, formatted, well contextualized, easy for wallets to decode and display to the user data, but also just slightly more interesting and usable signature schemes, such that like somebody who is, as I say, using a contract as a wallet can still sign messages in an easy and flowy fashion. So we have code for all of that, and in fact, the beautiful people at Open Zeppelin also do too. And if you're going to be using this kind of approach of signed data of any, which has to do with anything in your contracts, whether you're building NFTs or not, I highly recommend 1271, because it's the latest, and it's not only does it get you this formatted data, it also allows for like more complicated signing schemes, such that people with social recovery wallets, which we really like and highly recommend, they can use this too, which is important. So that's the basic kind of overview. There is a lot more to say about Merkle trees, which you're gonna have me come back, and I'll speak a little bit about Merkle trees and theta notation and log of n and leaves and nodes and other random words that I'll just stir around into some kind of soup and see what we can cook. But if Angela is willing, perhaps we can dive into the implementation of these 3 different ways of signing data, look at what a contract would entail with this kind of thing, and then we can get back to Merkle trees.
Yes, I'm very willing. I'll just share this notes doc that I had prepared. Eventually, we'll have it all on the Guild repository, but right now everything is in this Notion page, and it'll be nice if you'd like to follow along, and like this is the flow that I'll be following, and if you'd like to just read it in your own time, this can be helpful. So so to start with, whatever Andy mentioned are the techniques and strategies that we'll be focusing on. And the way we'll go about this is that I'll just share my screen. Okay, so the way we'll go about this is we'll just focus on this one primary challenge that we'll have of minting to a certain set of people. So up until now, let's say the Babel contract that we have worked on in the past 3 sessions, we have been able to create an NFT contract, and we have been able to mint tokens to certain people. Now that minting function isn't public, it's private. So Now, what if we want to, what if I, as an artist, I want to distribute my NFTs to a certain set of people, but I don't want to make it extremely public. I just want to limit it to a certain set of people. So we'll be focusing on this particular kind of use case. And all of the strategies that we discussed up until now were around this use case. So right now, so this is the first problem that I have. I have to distribute NFTs, but it shouldn't be claimable by everyone, only to a subset of people. So right now, what I can do is I can mint these 10 NFTs for the 10 people that I have in my community, paying gas fees for each minting transaction. And these two steps is something that we can do right now with what we have learned in the past 3 sessions. Now, what if I don't want to pay that gas? In that case, I need an efficient way for the smart contract to allow or disallow people based on who is claiming their NFT. So this claiming process is something that can be done either using signature method or the Merkle tree method. So the technical implementation. So if I talk about the personal sign method, it's actually just telling my smart contract that if anyone tries to mint an NFT, if they have this certain secret that I'm telling you, and if you can confirm that they have this certain secret, only then you should be minting the NFT. This is what I'll be telling my smart contract. So the way I do it is by giving a signature to each of these 10 people. Now, all of this use case is based on having Alice in our mind. So now Alice doesn't want to pay gas fees, but she has these 10 people. And what she does is she basically distributes 10 secrets to these 10 people based on the 10 NFTs that they can claim. And since each secret is unique to each NFT and each person, what this allows Alice to do is she can actually craft extremely unique NFTs for everyone. And whenever the recipient wants to claim, they can claim in their own time. It's not like she'll have to set a deadline or something for everyone's claiming. So, so like Andy already mentioned, there are these 3 techniques that we can use in case of distributing secrets. So these secrets are just signatures. So I can write it on a piece of paper and I can paste it and just send it over to these 10 people. And what I'll write and in the language that I'll write is determined by these 3 different strategies of signatures, which is personal sign, sign typed, and ERC-1271. And this is like one subset. So this is just sending secrets. And then there is this other method of that Alice can use to tell her smart contract that this time she isn't really distributing secrets. She is just telling smart contract about a certain, you can think of it as she's giving her smart contract a certain string. And whenever someone tries to claim, they are just bringing their identity with them. But if that identity matches that string, that is only when they can claim. Now, this is something that I'll be explaining in the Merkle tree section. It's a little complicated at first, but it's actually pretty simple in implementation. But first, if we talk about the signature method, this secret distribution. So personal sign is something, is the simplest form of signing a contract. What this allows you to do is, maybe I'll just open this, okay. And since I don't have a slide deck, maybe I'll just explain like this. So let's say this is a secret message. And Alice now wants to send this secret to one of the users who'd like to claim it. So what she'll do is, maybe let's not just focus on sending this, let's just focus on signing this message. So what the personal sign method does is it takes the string, and we're just talking about the personal sign method, which is a Web3 native method. And what this does is it prefixes this with some bytes. I think it's 0x19, and Ethereum signed message and space, and then this is a secret message, and then it hashes this entire thing using SHA-256, some hashing mechanism. And what we get after this is a really long string of just junk. So what this allows us is that this is particularly unique based on the message that has been signed. So this is just about signing a message. Now, what Alice is basically doing in the method that we talked is she has these, let's say this is her community of people, and all of these people, she wants to send them a secret. And there's a secret specific to everyone. So she wants, so she basically predetermines all of the token IDs that all of these people will have. So let's say this person is going to have 1, 2, third token ID, then this is the fourth, and this is the fifth token ID. And the secret that she'll give to each of them will be based on their address and the token ID. So their address is basically the identifier of the person in her community. And let's just call this thing Alice. Okay. And we have their address. This can be anything. And similarly, everyone has their own address. So what she does now is she has her own signing mechanism, and she basically does this for everyone. And she takes these two things, signs by her own private key. And so the way it's signed is, so let's just call this thing data. And the way she signs it is data, and Alice's private key gives us the message, the secret. So these kinds of secrets, so these are the 5 different secrets that she'll generate but using her own private key. And what next is going to happen is that anyone who wants to claim their token, they'll take this secret and they'll take this secret to the smart contract to claim their own token. And if I have a smart contract over here, once the secret reaches the smart contract, the verification happens on this contract, which will take this secret and it'll take the data. Now, as I mentioned, data is basically just this, the token ID and the address of the user. And what the verification will give us is Alice's public key. And what we get after verifying should be Alice's public key. Now, in this entire method, if you look at it like from this view, maybe, yeah. So as long as all of this data is generated in exactly this manner, meaning that only Alice is the one signing these messages, signing this data, and only it's her private key being used here. And the data is also specifically just the token ID and the person's address, the secret is going to be valid and verification is going to pass. But if it's signed by someone else's private key, or if, let's say, this person, the first person tries to create a signature for a different token ID, the secret is going to be changed and verification isn't going to pass. So this is how the smart contract can verify if the claiming request is valid or not. And this is what a signature does. And this method of creating this secret are the 3 different methods that we talked about: the personal sign 712 and the 1271. So personal sign is this is what personal sign does. It gives us a simple hashed message. What EIP 712 does is, as Andy suggested, it basically creates a typed data of all the secret. So I'll get into the demo, but I just want to make sure that this is clear. So the difference between these. So what is usually recommended is, if, let's say, you are implementing this strategy of distribution in your smart contract, currently the best kind of way that you can do is using sign typed data and not personal sign data, simply because it offers a much better UX. And what I mean by UX is this. So when you use a personal sign data, when the user, or when, let's say, Alice is signing her message, so you'll be creating an application for the artist to sign, or in any case, whenever you use a personal sign message, this is the left side of this image is how the message is displayed. And this is not the most friendly way of displaying a message that you want to sign using your private key. And what 712 standard allows us to do is create a message that is much more pretty and nice and everything. So in the demo that I'll be showing next, I'll be using sign typed data. And what we'll be doing is we'll be doing exactly this. So Alice, the creator of the smart contract, will be creating different secrets, and these secrets is what users will be using to verify and claim their token. And the implementation it includes just one more step where Alice can also define certain set of roles in a smart contract. It's nothing different from what I've just discussed, and I'll be showing you in the demo. So this is where the previous lesson ended. We had a Babel contract and we made it ERC 721 tradable, and it had a token URI and everything. So what I want to do is use this to just explain the concepts that I just discussed, and then show you what the final form of the contract will look like. So in terms of the concept, so maybe I'll just copy this entire thing, paste it here. And okay, so we don't need this for our contract today. We really don't want to make it tradable as of yet. We can add it, but let's just remove it for now to include simplicity. Sorry, to make it simple. Why would I include simplicity? Okay. So we have this, and let's just make it, okay, so we have, let's just let the contract URI remain where it is. And we want to make it an ERC 721. So maybe I'll just copy the import statement from here, and I'll make it 721. I'll also add an access control thing. So what access control is like I said, so Alice is signing those messages. Now, maybe Alice doesn't want to sign, and maybe just Alice appoints someone else to sign those messages. Or Alice is not exactly a single artist, it's a group of artists, and anyone can sign these messages. So what access control, OpenZeppelin's amazing library, allows us to do is it lets us create roles for different addresses. So there's one owner contract, there can be another community member address. So Alice is the owner who is deploying the contract. Then I can also appoint one other address who is a community member. Then I can appoint another address who's just a minter. So these kind of roles is what I can define using access control. So that is what I'll import. I don't really remember where it is, but maybe I'll just check in node modules.
I think it's utils.
It's utils? Contract,
maybe not.
utils. We can check here. It can be in, actually it should be in access. Access
yeah.
control. Access, and we have access control also. And contracts, access control also. Okay. And then we'll also make it access control. But even before defining roles and everything, I just maybe I'll just mention what is. So in this contract before, we didn't have a public mint function. So first of all, we'll want something like mint token, or let's just call it claim, because we are allowing people to claim their tokens. Just a second. Okay, so yeah, so we make it public, and it returns, maybe it returns, let's just focus on the code right now. So we have a claim, and in this claim, since it's public, we want users to tell us the token ID, because like I mentioned in my little diagram here, that each user will be having their own unique token ID. So maybe let's just add a UN256 for token ID. And what if I just call SafeMint here, and I maybe just send message sender this token ID. This is okay as long as we want the entire public to be able to mint tokens. So we also want to include the little secret that I mentioned. So if I include the little secrets here, I'll add bytes, call data, and the secret, or I can call it signature. And if the user is presenting the signature, it might not be the case that they are using their own address to send the signature. It can be a smart contract address that they are using. It can be from an application that they're sending. So basically, it's a best practice to not use message.sender here and include a address account or address to here. This will be the address that the token will be transferred to. We can use message.sender if we want to, but it's usually just a best practice to add the to here. So what it'll come down to is this. We still have to verify the signature. So we definitely need a require statement here. And what this require statement will do is we'll have to write down certain verification, like one verification function that will allow us to do something like this. So which I mentioned here. So what the user is presenting the smart contract is the secret and their identity. Their identity is in this data. And what this smart contract will do is it will try to retrieve a public key from that signature, the digest that it gets, and it'll be verifying if it's a minter role or if it's the default admin role or something. So we need to verify the signature, and we need to verify this token ID, and we need to verify, let's say, two. So this is what it has come down to. We have a require statement, and if this require passes, we'll be minting the token ID to the particular address. So the digest that we get is from this token ID and their address. So we'll have to generate that digest first before we can verify. So let's just add another function that we'll be implementing here. What it'll take is it'll take a token ID and two, and let's just remove token ID and two from here. And this is what we have. So basically and let's just make both of these private this way. So now we have to implement two functions. One is the hash function, which takes token ID and two. It creates a digest, and that digest along with the signature is what the contract will use to verify. And that's about it. So in terms of, wait a minute. Yes, here we were. So in terms of implementing the personal sign strategy from Alice to her community members, this is all the addition that we had to make in our smart contract. There are other few details that I'll be mentioning in the final smart contract and what the final code will look like. I'll be discussing that next. But in terms of the logical additions, this was the main important one. And the flow is something that I already talked about. So off-chain signature generation is what Alice will do, and people will send their secrets to the smart contract. And I'll just show what the final contract will look like. So there are a bunch of libraries that have been added over here. I'll be discussing that next. But before that, also one more thing is that this hash, we have to make sure that this hash is verifying according to the EIP SEN12 standard. So this is the reason why we have this draft EIP SEN12 library. This is what it helps us to. And we have this ECDSA library, which is what will help us in this function. So hash and verify is something that we'll be implementing using OpenZeppelin's libraries. And that's okay. So getting on the final version of the code. So this is what we did right now. Instead of, you can call it secret, proof, or signature, whatever you want to call it. It is that little string that people will bring to the smart contract. And we also give a reason if it throws an error, and then we have this SafeMint. So the way hash is implemented to actually understand exactly why we are using this over here and we are using this particular function, and why we have included a random version on top, is because of this standard, EIP 712 standard. So when we generate a signature using EIP 712, the three most important things that we have to include are, just a second, I'll just show it and that will be better in explaining. So I have a signature, like I'll be going through the test cases in a minute, but before that, let's just focus on these three things for now. Maybe I'll just zoom in. Okay, it doesn't move around. Nice. Okay, so let's just focus on this. Whoa, my laptop is slow. Okay, so we have a domain, we have types, and we have value. So domain is specific to the smart contract. Domain is what connects the client request for the signature to the backend or to the on-chain smart contract. So this is where we give the name of the smart contract, the version, and the chain ID and verifying contract. The reason the chain ID was included was because it was extremely easy to use the same signature from Ethereum chain on, let's say, Matic chain in the personal sign era. So when there was just the personal sign signature standard, so maybe I'll explain it with an example. This is what I came across, and we experimented with while I was at Matic. So at Matic, we had these two different test networks. We had the beta network, and we had a Mumbai network, which was another test network. And since everything is get based, we had any get address will be valid on all get chains. So your Ethereum mainnet address will be valid on Matic's other chains as well. So an address that has signed a message on, let's say, Matic's beta network, I can take that exact signature and I can try executing it on Matic's Mumbai network. And since the private key will be same, the derived public key will be same, the derived Ethereum address will be same, the signature will be valid. And that signature can be executed. This was the reason why MetaMask had started giving a huge red warning whenever you asked the user for a personal sign message. And this is why the sign type message came into being. And this is why we include the chain ID in here. So it's actually best to include chain, like not hardcore chain ID, either in smart contract or on frontend, and just include, retrieve chain ID from the chain. The verifying contract is the address of the contract. So this is what is domain specific. Then we have types. So in our contract, we just have one type, which is the NFT that we are trying to claim. We can have different types, and let's imagine a gaming contract where you're not just claiming an NFT, you are also claiming, let's say, some ERC20 tokens. And in NFTs also, maybe you're not just claiming one type of NFT, you are claiming your NFT award, you're claiming your NFT costumes in the game, or like all of these other types. So we can actually specify these types, and these types is what will be displayed like this over here. So this is why the types were included. So the user knows exactly what they are signing up for, literally signing for. And then we have this value. So whatever we specify in types, the token ID, account, and all of the names that we specify in types is the value that we'll be passing when we want to sign the message. Is Andy, are you saying something?
You're good. Carry on. There's a few comments, but we'll clean them up and get to them when you're done here.
Actually, yeah. Before starting with Merkle trees, I'm hoping to take a look on the chat and answer a few questions. So okay. So back to our smart contract. So this is the reason why we have added the version here. because of EIP Send 1.2. And this is how the claim is happening over here. And in terms of this hash, like I mentioned, hash is basically taking the data and trying to generate the digest for which will be verified against the proof that is provided. So that is what is happening here. Anything that we gave in the types in the front end is what will be used in here. So since we gave NFT there, NFT will be used here. And that's how the digest is generated. And in terms of verification, we take this digest, the hash that is generated over here, and we take the proof. And it's really super simple. So verifier will just return if what it has recovered from the digest and signature is actually a minter role or not. And I haven't gone into how exactly a minter role is specified, but I'll get into that next. But this is how the verification is happening. And if what the signature gives us is a minter role, that is, so this verification returns true and you are able to save mint. So in these three functions, what really is happening is that, let's say we have Alice, Bob, and Charlie. So Alice deploys the smart contract. Alice provides Bob a minter role. So this is one on-chain transaction. And then Bob creates, let's say, 5 or 6 secrets on off-chain secrets. And the way he's creating these secrets is by signing those typed messages that I talked about. So once we have these 10 different strings, these 10 different strings are distributed to all of these 10 different users. And what those users will do is users will take that string, they'll bring their address, and they'll bring the token ID that they want to claim, and then they'll call this function. So users' interaction is based entirely on the kind of front-end application that we designed for them so that it's seamless for them. But that is what is happening underneath. And yeah, so this is what is happening. So we, and in terms of, now the last final piece in this entire contract is the access control and the minter role that I talked about. So it's really simple. So if you're already familiar with the ownable contracts, you can think of ownable, but like even better terms of admin controls that we can give to a smart contract. So instead of making it ownable, we can just add access control in here, and we can define all of these different types of access that we want to have. So in this particular contract, Alice didn't want to create those signatures. Alice was maybe part of an group of artists, and she wanted everyone to have this minter role who can generate these off-chain secrets. So this line is what defines a role, and in the constructor, or once we have deployed the smart contract, we just call grant role function. We'll get to the testing part, and that is when I'll show the exact execution of it. So what this constructor is doing is it's just giving an admin role to Alice, but Alice can give other roles to other people. Maybe I'll just run the test cases once, and then I'll get to what the test cases look like. Here is the test case for the entire contract that we talked about. So all of the functions and all of the entire flow that I mentioned from the graphics and right now is what these test cases include. So this is weird. Oh, Babel V2 is something that I just created. So maybe I'll just delete this. And we already have the announcement. Okay. So what we are doing in these test cases is So the first thing that we are doing is we are assigning a mentor role that I talked about. So Alice deploys the contract and she assigns a mentor role. So this is completely optional, but I'm mentioning it because usually it'll be a group of people trying to create those secrets for other people in terms of a bigger community. So even let's say we are trying to distribute an NFT in kernel, we are 4 stewards who will be generating these off-chain secrets for all of the other people who will be claiming their NFT. So this is why it's usually better to include an access control in your smart contract. Then there is minting happening. So Bob, who has got the mentor role, is able to mint tokens, and he also signs authorizations for Charlie and Derek, and Charlie and Derek are able to claim. So I'll just get into the exact part of the code to mention, to discuss what it looks like. So in giving a mentor role, like I said, so it is usually just this. So Alice calls the smart contract that she just deployed, and she grants a particular mentor role to Bob's address. And in terms of minting, Bob is signing this typed data that we discussed. And this type data is what is being used by Bob to claim that NFT. And this is exactly what is happening in Charlie's and Derek's case as well. And since we are using address in this in the claim function, and we are not using message.sender, so even if some other address tries to call with the same signature, it's not like that address will receive the token. It'll be the address that is retrieved from the signature and that is verified that will receive the token. So that's about it. So maybe I'll just take the questions, or maybe just go through the chat ones before getting into the Merkle tree distribution mechanism.
And so that there are a few questions. The first is, what font face are you using in your terminal? I mean, in your VS Code.
I am using Cascadia code and I love it. I absolutely love it. It's completely open source. It's provided by Microsoft, and I'll just share the link where you can download it. Microsoft Cascadia code. This, okay. I love this font.
Well, you grab that. The next question is from Alan, and it is about well, yes, you know, it actually came from somebody else first. Why do we use the address rather than just message sender? To which, you know, the answer is that sometimes they differ. And Alana asks, can we explain a little bit more about why, for instance, sending a message from a multi-sig account might cause the difference between message.sender and the address too? And also, if there are ways of giving an NFT multiple ownership, having like a multi-sig NFT instead of just one address being associated with a token ID. Are there ways of associating multiple addresses with one ID?
Okay, so actually, this particular contract that we have constructed and we are talking about doesn't really show the exact use of why we are using this address over here and we are sending this to that address. But usually in contracts that require like much higher level of authentication, authorization, and security, we want to send it only if the verification has passed. So in this case, we are simply just verifying if the signature that has come from this data and the proof is from a minter role or not. But usually we actually want to get deep into the exact data that was signed on. So let's say Alice actually authorized a different address, and so let's say Alice authorized me to get the NFT, but Andy is trying to use my signature to get that NFT. So in Andy's case, he wasn't authorized, but he has the signature that is from a minter role on the contract. And if the contract uses message.sender, Andy will be able to get the token, but it shouldn't be the case. So this is why it's usually best to add the address in the contract call, in the function call, so that after verification you can actually send it to the exact address which it is intended to go to. But in this case, we are not really getting into the security specifics of this thing. So this is why it's not really evident or obvious here. And in this case, I could actually use message.sender. It wouldn't have been very different. And this is why I mentioned that it's a best practice to use that.
Multiple owners of one NFT, multiple addresses associated
Yes.
with one token ID.
I don't think that is not doable. I mean, that's definitely doable. You can like Alice could sign in this particular example that we were talking about. Alice could sign on this address, which actually didn't belong to this one entity, but actually belonged to 3 entities, and it was a multi-sig account. And they should be able to send or receive. But I think I haven't actually ever dealt with this kind of thing, but I'm guessing it's similar to the way ERC20s are handled in a multi-sig account, where you need M of N signatures to be able to pass that transaction. So maybe if you want to transfer the NFT in the multi-sig, from the multi-sig, you would need M of N, and something like a Gnosis safe account might be able to handle that. So I don't think it's impossible. It's definitely possible, but I don't really have the deep technical knowledge of its implementation to tell you more about it.
Wonderful. We'll continue with that question another time. Yeah, hold on, because there's some other things. Erin has been asking just a little bit about your VS Code extensions, how you have these function traces and the little arrows next to your types, like where you got them, what they mean.
Okay, so if you're curious about these errors, so this is coming because VS Code is not able to find the
no, Angela, sorry. Like literally above each function, there's that little gray line that says ftrace and func.
This.
And the little arrows next to like interface ID and that kind of stuff. What are those? What do they tell you as a shadowy supercoder?
Okay, so usually this is so if I'm using this this particular variable inside my function, this is when this arrow comes up. I haven't actually delved deeper into why exactly it comes up, but this is what I've observed. So if I remove this, and if I don't use that particular variable, the arrow goes. But if I enter it, it comes up. So this is how I use it when I'm coding, that if it's showing up, then it's fine, I'm using the variable. But this is a good question. I should actually be more mindful of this. ftrace is, I don't think it's working right now. But what it usually does is, I think you can actually see it in Etherscan also. So it allows you to trace the function call. So it's actually function trace. So where exactly is this imported from, or where exactly is this overridden from, and how exactly are the calls happening? So usually, so in this particular example, we are just implementing a function and then calling a function. Usually it can go much deeper than that. We can have a function introduced in one contract, which is inherited in this contract, which is actually an internal, and it's not being called here, it's called somewhere else. So that is where the function tracing is used. I'm not actually that big into debugging contracts that I could give you an example. I wish I could, but this I know is that
we
this is
actually
where
ran into an example last week, which was that when we were implementing the OpenSea proxy, you will remember that prior to version 4 of the OpenZeppelin contracts, the override that it was using in set approval for all was not having the intended effect because of a less than considerate implementation of override from the OpenSea team, which OpenZeppelin then had to fix in version 4 of their libraries. So that's like a good example of override in particular is like a very dangerous word, I think, to use on your functions. And if you're not careful of like where that override is coming from, how it's overloading the function, this kind of stuff, then it can be difficult. And being able to trace the function is a really useful feature.
That is true. And if you're also curious about function sig, it gives us the function signature for your each function. So it's actually just a hash. I think it's the first 4 bytes of this thing. So it includes the type of the argument, not the name of the variable, the type of the argument and the name of the function. This is useful in knowing. So when you deploy your contract, and if you don't verify it, sometimes ethers can actually use these function signatures to match with function signatures in other contracts in its entire database to generate some version of your smart contract. That is one particular use case of function sig, but there are more. So are there any more questions? I don't see any actually. There's one that was asking me to zoom out on Excalidraw. Maybe I can do it right now. And oh, actually wait. This is my beautiful drawing. Yeah. Is there, should I go ahead, Andy?
Yes, you should.
Cool. Okay. Where were we? Yes. So up until now, what we have been able to do is that, let's just open this again. Yeah, so now Alice is able to generate these 10 different secrets to distribute to 10 different people who are now able to claim their token from the smart contract. And this claiming mechanism is something that I'll just be showing the code and what we did in our case at kernel. I don't think we'll have the time to delve deeper into it. It's not Web3 related, it's entirely a front-end application thing. So how seamless you can make it. So this is why I'll just be briefly touching upon it towards the end. So this was one mechanism of allowing or giving Alice this way of distributing her NFTs. The other mechanism that she can do is in case of a huge number of receivers. So let's say it's not a 10 people community that Alice is running, it's actually a 10,000 people community, and she's not that good in scripting and she doesn't know how to generate these 10,000 signatures at once. And also, like, even if there are 4 people inside the community as admins, they don't know how to do it. So the other method that is available for distributions like these is where Merkle trees come in. So before getting into Merkle trees, the reason why we are looking into this is that in terms of, like, in a case where there are a large number of receivers and we don't know, let's say, we don't know which token ID to give to whom, or in a case where we don't want to create these signatures, we really are just looking for an efficient method or mechanism where once a user takes their identity or takes their data to the smart contract has a super quick way of knowing if this is an authorized address or not, where the request is coming from. And for smart contract to be able to do this, we really just need a very efficient data structuring mechanism. So there are like different data structures. We have linked list, stacks, queues, and we're just looking for something like that, which has this special property of lookup, like really fast lookups, and is not super huge on storage. So we don't really want to store all of these addresses. We just want to know if it belongs to the set or not. So a structure like this already exists and is called a Merkle tree. Now, Merkle trees are used in a lot of use cases. Like right now, Andy has already talked about them a lot. So maybe I'll just briefly touch upon the concept and everything. So there's this other diagram that is over here. Maybe I'll just zoom in. So yeah, so this is what a Merkle tree looks like. It's actually upside down, so it's a reverse tree. So it's usually a binary tree, which means that each node has maximum of 2 children and 2 branches. And if so, in this case, we like I very conveniently added even number of leaves in here. So these things, maybe I'll just make it green. And yeah, so these things are leaves. Leaves are the final most node in a particular tree. Even if we're talking about binary trees or aerial trees or whatever trees data structure that we're talking about, the wherever the data starts from are called the leaves, which have 0 branches. And these are our leaves. And in this case, we have even number of leaves. Or so basically, even number allows us to create these pairs, which are then combined to this parent node that they form. So, and in case of an odd number of leaves, the way Merkle tree works is that the final node is duplicated. So basically, if this were an odd number, what Merkle tree would do is it'll take this thing. Wait a minute. Yeah, so it'll take this last node and duplicate it just to make it an even number. So what happens after they are an even number of leaves that we have got? Each pair is formed between, so let's say these two form a pair, and then these two form a pair, and then these two form a pair, and all of these pairs are combined to form a parent node. And then again, pairs are formed to form a parent node. And the way these pairs are formed is by first creating a hash of all of this data. So like this is a little complicated of why exactly we are doing this, but in terms of storing something in a computer system or in a network, or like wherever we want efficient storage and efficient verification of things, we use hashes. And this is why all of the transactions in a blockchain network are hashes, because any little thing that we change in the underlying data changes the hash, and hashes are much easier to store than the actual data. So the first step is what a Merkle tree does is it takes the leaf node, it converts it into a hash, and these combination of hashes, these pair of hashes, just keep combining. All of these pairs keep combining to form another hash, and then these other pairs keep combining to form a hash up until a time where we have just 2 hashes which combine to form one single hash, and that is our Merkle root. So this entire thing that we have now is a Merkle tree. And any data that we change in one of these leaves, even if I change the E, this particular E to make it a capital one and not a small one, the Merkle root will change. So this is where a Merkle tree is very efficient. So this is why we use it in places where we want to verify quickly, because any underlying data that changes will change the Merkle root. And this is how actually the data is stored in a Bitcoin blockchain. So I think even in Ethereum blockchain. So all of the transactions that happen and all of the transactions that combine to be included in a particular block, all of these transactions combine to form a Merkle root. And that Merkle root is referenced in the next block of the blockchain. This is how the blocks are connected. They are connected via Merkle roots. And any root that is being changed in, so you can imagine, this is why it's extremely difficult to change data in a blockchain, because any data that you change in one of the blocks will change the Merkle root. And that Merkle root will have to be changed in all of the coming chains or coming blocks in the blockchain. So this is the data structure that makes blockchain super difficult to be changed, to be mutated. So, yeah, this is how, this is exactly what the data looks like in a Merkle tree. And the reason why we are using this for extremely fast lookups is that you can imagine just by looking at it. So if I give you, like, if I give this system a hash of, let's say, if I want to find sum, and if I want to make sure that sum is included in this Merkle tree that is rooted at this particular hash, the maximum amount of lookups that will happen here in big O terms is 2 log 2n, which is actually just the height of the tree. So it's not like it is checking against each and every data that we have. It is actually just checking against the maximum height that the tree has, which in a binary tree is always log to the base 2 of n. I don't know how to add base here, but this is why. So that's the big O notation. So otherwise, this is why we use it. And if there are any questions, I can take them right now in terms of Merkle trees, or otherwise I can just get to the implementation of how we use this special data structure for airdropping our NFTs.
I think like a nice way of just explaining that reason why it's so easy to look stuff up in it and why it's really just got to do with the height of the tree. Just intuitively for you, if you're struggling with that and you've never seen big O notation or log base 2 freaks you out or something, like one of the like neat ways of thinking about this is that when you look for a person's name in a phone book, you don't have to flip through the entire phone book to try and find their name. You know that you can look alphabetically by the first letter of their surname, and then you're doing increasingly smaller little steps to find that particular person as you go. Okay, like it's Gilhotra, so I go to G, and then I look GI, and then I look GIL, and then I look GILH, and I get closer and closer and closer to the surname that I'm looking for in what is called a log n way, right? So when we have something called like theta n, it means that like the time it takes to search for data in that structure grows linearly as the structure itself grows. But when we have theta log n, it means that it grows logarithmically as the size of the data grows, which is much smaller than growing linearly. And it's nice to imagine like this phone book searching, because like that's what you're doing in this Merkle tree, right? You don't have to search the entire data structure. I know that I'm looking for sum, so I just have to go down to the left branch 0x46, then like 1 to the right, which is not written here, and then like 1 further down. And that's just like an intuitive way of thinking about like why this lookup is only based on the height of the tree as opposed to other data structures, which have other features, but not this really nice O of log n lookup speed.
That is true. Also, for the question in the chat right now, if the Merkle tree is sorted by something, it's not, but the sorting changes the root. So the root and all of these hashes are also dependent on the exact sorting of the underlying data. Because you can imagine these pairs are being formed based on their sorting. So it can or cannot be sorted, but if it is, the root is dependent on it. So yeah,
it's much more efficient if it is sorted, because then it doesn't matter whether it's like left-handed or right-handed. You're not concerned about the neighbors on either side. It's just you'll see in any implementation of Merkle roots like that we cover in this course or just in the wider Ethereum ecosystem, people generally always have like sorted true.
Exactly. This is what we have in our implementation as well. So okay, so in terms of starting back again from where we left in the last session, I'll not be starting from where we left in the last section of this call of this session, because it's completely parallel way of distributing. So it's not dependent on signatures. Signatures is one way, and the other way is Merkle root. So let's just take this and maybe let's just create another Babel v3 or something. And we will remove this, and it's just ERC 721. And we'll also remove this just for simplicity. Okay. And the next thing that we have is, so in terms of making the smart contract aware of the Merkle root, we want to include the Merkle root inside the contract. So maybe let's just add bytes Merkle root. And this is, let's just make it a public variable. And each time a claim happens, we want to check if the proof or the signature that the user is bringing with them is actually a leaf of the root or not. So first of all, when Alice deploys the smart contract, so in here, now Alice has two choices. So if her community is exactly what it is, so if she has just 10 people that she ever wants to distribute this set of NFT, then she can make this an immutable variable, which means that the Merkle root is never going to change. It's going to be the same thing. And she can pass in the constructor she can take the root in the constructor, and she can set the root right at the time of deployment, which will make it immutable. And as soon as it's out there, the contract is deployed, the Merkle root is set, and only the people who have been included in the Merkle tree will be able to claim that NFT. Like for now, let's just assume that the Merkle tree, the data that we talked about in here, so for Alice, she'll be constructing this tree based on her community. So the members of the community, the identifier that she has. She can either have Ethereum addresses for her community, or she can have their email addresses. Any identifier along with the token ID is what will generate this Merkle tree. And we'll get to the generation next. But for now, let's just focus on the logical changes that we'll be making to the smart contract. But before that, I need just 1 minute to put my laptop on charge.
While Angela does that, the reason that you would use an immutable keyword here has to do with gas savings. When we use immutable before any, or after any, in fact, sorry, before any variable declaration, it copies whatever the value of that is into your code everywhere at compile and deploy time. So it's not actually stored in storage. And so you can achieve quite significant gas savings by using this immutable keywords for things that definitely will not change. So yeah, that's why you would use
it. Okay, so so now that we have the root set, the next thing that that Alice would want to do is make sure that the root that make sure that any claim that is coming from anyone is a part of the tree. So it's basically exactly what we did last time as well. So in here, it's going to be a pretty similar looking function. And just a second. So it's going to be a pretty similar looking function. We're going to have a proof. Now, instead of generating a hash, we'll actually be just generating a leaf. And we'll be verifying if that leaf exists in the tree rooted at this particular root. And if it's not, it's going to give an invalid Merkle proof. And in terms of a Merkle proof, we actually usually give an array of bytes 32. That is actually just the way a Merkle root is implemented. And this is how it works. So we generate a leaf, and the proof is an array of bytes 32. And we check if that leaf is a part of the tree by taking in that proof. And if it is, the minting is completed. And if it isn't, the minting isn't done. What the final form of the contract will look like will be this. So it's basically what we just talked about. So it's a simple ERC 721 and the Merkle root is being passed in from the constructor as soon as the deployment is done. And like I said, so first of all, a leaf is generated. And leaf is just this. It's just the hash of the data that we get. And the way you can think about I'm not sure if this encode pack was already covered in the previous lessons, but it's actually it's exactly what the function says. It's packing of the arguments that you give it in the form of in a way that Solidity will be able to understand. So token ID is a UN256, and account is an address. So underneath, what it actually does is it combines these two arguments into a really big string that that is representative of what of the type of variable that they are. And so address, so yeah, this is a token ID, account, and the Kechak 256 is the hash that is formed. And this is what the leaf is. Verification is basically as simple as this. It's actually pretty complicated underneath, but again, the library that we'll be using by OpenZeppelin makes it super simple for us, which just verifies if the proof that we have got is valid for the leaf, and the leaf is the part of the root or not. If you want to get to the details, maybe we can see what exactly the Merkle proof or the verify function looks like. So you'll be able to see it in OpenZeppelin's node modules.
Utils cryptography.
I keep forgetting that. Cryptography, Merkle proof. This is like a single contract with all of the functions that we'll ever need. And this is what we are using in here. So like I said, byte 32 is an array of, so the proof is actually an array of bytes 32, and there's a root and a leaf. And what for each element in this array, the computation is happening. So what it actually is doing is, by going step by step around each of these array elements, is that it is trying to calculate these hashes that we talked about one by one until it reaches the root. So if it reaches the root, which the verification function has got in one of the arguments, then the leaf is a valid addition of is a valid part of the Merkle tree. And if it isn't able to reach the root, if it reaches a different root, it's not a part of the Merkle tree. And this is why we call it log base 2n, because the maximum number of times that it'll have to do these computations is the height of the tree. So so that's how it's happening. And so if I get to the test cases, I'm not sure. Actually, it's a really small test case scenario that we have here. These are the members that Alice would like to send these particular tokens to. So so Alice has this entire community, and Charlie and Derek need to be able to claim these tokens. And the Merkle tree is formed by these members. So actually, this one line, what it is doing is, it's I wish I had made it, I had not used map in here, but maybe I'll just add like this. Okay. So what it is actually doing is, it is taking these members, and the way this JSON is created is token ID and the address that the token ID belongs to. And the way this Merkle tree is formed is, it is taking these members and it is creating a hash of the token ID and the address, and then it is combining all of these hashes together. So if I were to show it here, the way it'll look is the token ID and address, this is hashed together. And similarly for all of the other ones. So this is for Charlie and for Derek and all of the other members in her community. So one Charlie is hashed together into this, two Derek is hashed together, and then all of the other members and their token IDs are hashed, and these hashes then combine to form this one Merkle root for Alice's community. And whenever, so that's about it. So this is how the Merkle root is generated. And that is what Alice uses to deploy her Merkle tree. So she gets the hex root, and because because all of the libraries are available, it's actually just a one-line implementation for us. But Merkle tree, to understand Merkle tree takes a little bit time, but to implement it is really simple. And that's how she's implementing it. And once it's there, and once the members are decided and the tokens are decided, she has deployed the contract. Now, whenever someone wants to, so whenever Charlie or Derek want to claim their token, they just simply take their token address, their token ID, and the proof. And the way proof is generated is by hashing. So it's actually just calling a single function and then hashing their own token address and their own address. These two functions is something that the user should never do themselves. It's actually handled on the front-end application by the developer. So this is what the last section of our talk will be, of how exactly to implement this. But this is how the claiming is happening. And maybe I can just show you what, while I run the test cases, if you have any questions, feel free to ask right now. I don't know the spelling of hard hat. Hat.
If there are no questions, I think it's worth just reflecting a little bit more on the facts of how, once again, we come up against a scenario in which there is an enormous amount of underlying conceptual complexity that is dealt with by these wonderful Open Zeppelin libraries and the collective consciousness of all of the different developers that have worked on this kind of stuff. So, you know, it's really, it's a lot to take in a session like this when we're going through the deeper underlyings and speaking about log-based 2N lookups and all of these kinds of things. But as Angela has demonstrated, the actual implementation of these kinds of things is really, really simple. And if you have stayed with us and have been following along with a lot of this kind of stuff, one of the other things that you will notice, particularly in these wonderful tests that Angela has written, what's kind of most fascinating for me is that this particular method of doing things is actually the most gas efficient. The Merkle tree, you know, the cheapest ERC 721 contract to deploy is just the basic contract with none of the tradable stuff that we did last week, none of the other sort of fancy bells and whistles which make for a good user experience. It then gets progressively more expensive from a gas perspective to have signed data, then to have personal sign, then signed type data, and then 1271 smart signed data. And then in fact, it turns out that this Merkle root method is the cheapest apart from the basic ERC 721 method for deploying these kinds of contracts. So it's certainly the method that I would go with, so long as you feel increasingly comfortable with what the hell is actually going on with this incredible data structure and how the proof is generated and how it travels across the heights of the tree. The other thing that Angela might consider speaking about, I'm sure she's going to get to it now, is when you don't want to have an immutable root, but that will come next.
Yes, actually, first I was trying to see if I can get this. Okay, wait. Okay, anyway. So in case where we don't have, like in case if Alice's community keeps on expanding and she doesn't really want to make it immutable, and not this, sorry. So she's not sure if the Merkle root is going to stay the same in a 1 month or 2 months time. That is when it's actually just as simple as setting up a function that allows her to update the root and get the root. That's about it. So this is already public, so we can get the root from the contract, but in case of updating, we'll just add a little function in here that is probably update root, and we take the root in here as the bytes memory, and we make it public, but we add the only owner, and that's about it. So this is what we do, and we just update root to new root, and that is what we're going to do. So this is like implementation wise, it's just one more function that will be needed, that would be needed to be added in the contract. And this is how the once the root is updated, the newer members will be able to claim their NFT. And maybe I'll just show the implementation of the gratitude NFT that we built some time back. And it's really just as simple as that. It has the set Merkle root and it has the get Merkle root, and the set just allows the owner to be able to update the root. And in this particular contract, we went ahead and implemented the verification, but at that time, the Merkle proof wasn't available. The library by Open Zeppelin, which is like really beautiful. And this is why we had to go ahead and implement the verification function that I just showed you in the library itself. But now that we have the library, it's just as simple as returning a verify function from the Merkle proof library. And so Andy, would you also want me to get into detail of how exactly the proof is happening? I just showed how it's happening over here. So
yeah,
do you want me to
okay.
do that?
We can always answer that asynchronously in Slack. I think it would be better to get on to how users generate claims and talk a little bit about that.
Yeah, actually, I'll keep adding that in this Merkle trees brief, because I didn't really want to step aside from the actual implementation of, because the entire challenge, like I mentioned at the start, is about distributing these NFTs and these different mechanisms. But if most of the people are interested in how exactly Merkle trees work, I'll keep adding it in here, and it should be updated by the end of day today or tomorrow in the NFTeasy repository as well. So you should be able to find all of the code and maybe some sample code in there, and the libraries that you can refer. The libraries that I have used are the Merkle proof cryptography library by Open Zeppelin and the Merkle tree JS for front end. And this is exactly what, if you were to develop your application from scratch, the front end of it, Merkle tree JS is what you'll be using as well. So that's about it in terms of distributing and creating these different mechanisms and structures for Alice to be able to distribute these NFTs to her community. Before going into the next section, maybe I'll just recap on what we discussed, and just like bringing the focus back to exactly what we wanted. The challenge was to be able to distribute NFTs to a certain set of people. The two ways that we explored were distribute unique secrets to each of these people, and the recipients take this secret and they go to the smart contract and they claim their NFT. The other method is I just tell the smart contract that these are all possible people with these all possible proofs that they might come to you, and the smart contract authorizes the minting according to that, which is the Merkle tree way. And in case where Alice doesn't know if the community is going to keep expanding or if it's going to stay the same, she might not want to make the Merkle root immutable. That is when she can make it changeable. So these are the three different methods that she can be used. The final thing is that how exactly do we close the loop here? So up until now, we have just been talking about Alice's side. So in case of like we mentioned, so Charlie and Derek are in Alice's community. So what about their UX and how exactly do they experience? The last section comes in, where now as a developer, there are like various ways that you can make the claiming experience seamless for a user. So I'll show the example of how we did in the kernel gratitude NFT. But before that, maybe I'll just mention that one method is the link drop mechanism, in which each user receives a unique link that they click on, and then that takes them to a particular page where they connect their MetaMask and then they claim their NFT. The other method is that maybe you just show a QR code. Maybe you are out there in a conference and there are some coffee cups that have a QR code, and you scan that QR code, and that simple scanning basically creates a proof, and then it also sends that proof to the smart contract, and then it sends the NFT back to you. Then there is another way where you can just create a login mechanism. You log in via email and then you click claim and then you get the NFT. So claiming is like entirely dependent on the developer, and it's an application specific question of how you want the claiming experience to be. It's not a Web3 related thing. This is why we won't be like going deep into it, but I'll just mention of like one mechanism, which is the link drop mechanism. And in this, so what the final form of the thing that we want it to look like is that, let's say Charlie receives this particular link, which is unique for him. So this can be any unique string, or it can just be the token ID, because like we discussed here, the token IDs are usually unique to the receiver. So this is the link that Charlie will receive, and once he clicks it, he'll be landed on a page that prompts him to claim the NFT, and that is how he claims it. Essentially, underneath, code-wise, what we'll have to include is once that page is opened up, we just need a method for our application to know the exact data to display, and that data is simply being fetched from on-chain metadata. So we learned about generating and storing metadata on RV or IPFS in previous lessons. So that is what we'll use here. And we just basically make one call to the contract with the token ID and fetch the token URI. And all of the JSON that we get is what we parse and display for the user. And that's about it. So, so maybe I'll just share what exactly the gratitude NFT looks like. So each user over here. So this is like a bunch of metadata, which might not make sense right now, but let me just try explaining what it looks like. So all of this is a huge JSON of 5,000 or so lines. And this JSON consists of a token ID and the image of the NFT, the external URL, the name for the kernel fellow that we wanted to gift this NFT to. The award testimonials are other things that we added. And then there is gratitude. So I might just skip the gratitude section because that was specific to the application that we were building. These are the attributes, which is again specific to OpenSea. But overall, this is what one token's metadata looked like. And in terms of claiming, the claiming experience that we designed was that each user has their own, this unique hash, which I've just highlighted. And this hash is generated from their unique token ID. And that's where this entire deterministic things keep coming in. So as Alice, we created all of these unique token IDs for each fellow. And then we created these unique hashes. These hashes is what will lead each fellow to a unique page that will display the token's description and everything. So this is what it looks like. And one such example of the claiming UI is this. So this Paul Gadi is one of the fellows, was one of the fellows, and is the gaming track leader. And this was his unique hash, which led to his unique token ID. And all of this, like all of this data is being fetched on chain. And this simple call that I mentioned over here is what is being used on the front end: contract.token URI and token ID. Token ID is what the application gets from the hash, and all of the metadata. By metadata, I mean this name, the award, the testimonials that you can see over here. All of this is on chain, and the chain is Matic that we had been using. And this is how it's being fetched. So on the front end, it's actually super simple. It's just one single function call that you have to implement. And yeah, that's about it. And in terms of claiming, I can actually, this is already claimed. So this shows that the token is already minted to this particular address. But in terms of claiming, maybe I'll just show the code of what the claiming process looks like. So a bunch of things were happening in the front end. Essentially, it was just a single click for the user. I can find actually if someone hasn't claimed it yet, but okay, up until then, let me just show what the gift looks like. So claim. This is the claim function, and this is what was happening. So when you clicked on claim, the first thing that happened was the image that, so this image was a generative art, and we didn't know how many people will be claiming, and we didn't have an efficient mechanism for storing all of these unique images for each and every user. So when you connect MetaMask, maybe I'll just connect and show. I don't want to claim this, but click it. And okay, yeah, so this is just one single click. But what this one single click does is, first of all, it takes this image and it uploads to a single server. And we haven't uploaded to RV, but it ideally should be a decentralized server or decentralized thing that you're uploading to. But right now it is uploading to our server. And once it's uploaded, that link is what OpenSea uses to display on its own end. So when you see the entire collection on OpenSea, that is where the image is being fetched from, because it's being uploaded at that particular moment when the person is clicking on claim. The other thing that is happening is the minting, and before minting, it actually also generates a proof in here. So this proof is generated as soon as the person clicks on claim. So again, this proof is the proof that this particular person is a part of the Merkle tree. And that proof goes to the smart contract, and the smart contract approves or disapproves for the particular claim. And yeah, that's about it. So this is what it looks like on OpenSea. We have all of the attributes in here, and this is what other tokens look like. And yeah, like I said, so the final section of closing the loop in terms of how exactly do recipients claim their NFT is entirely dependent on your application logic. And you can make it as seamless as you'd like, or the users can generate their proof themselves on CLI and use that to claim from the smart contract. But yeah, that's about it. So I've added like a few little more things in these dropdowns. Yeah, so if there are any questions, I'd be happy to take them now.
If not, we can talk just a little bit more about closing the loop on this particular guild both this session and all of the ones that have come before, just in terms of the cultural intent of this particular linguistic primitive that is now available to us, which began as an exploration into deeds. If you remember all the way back to session 1 and looking at the 721 standard in the EIP's repo, it was predominantly to do with property deeds, title deeds, these kinds of immovable assets. And it's really fascinating to me that it has morphed and changed in the mimetic environment that is the World Wide Web, and resulted in an explosion, and some might call it a Cambrian explosion, of artistic expression and cultural experimentation. I think that's, it's first of all with enormous gratitude to Angela that I say this, that, we have one of the most interesting implementations of this kind of thing, particularly to do with some of the metadata that exists around these tokens. And that has led us to certain kinds of trade-offs, like using our own server. But the images and this kind of stuff will be put on Arweave fairly shortly. But that kind of points to some of the engineering trade-offs that we've been talking about through the course of this guild. And it also, I hope, illustrates how early all of this stuff still is. That's it's such an exciting time to be involved in this kind of work, because while there are standards and while there is tooling that exists across the ecosystem and is incredibly, incredibly helpful, like we've seen today with the Merkle proof and ECDSA and 712 and 1271 data types that Open Zeppelin has implemented, there is also room for the most enormous kinds of experimentation. You can have NFTs with updatable token URIs if you're me and you want to write a book that allows owners of guardians of chapters to change whatever appears in that chapter. You can have updatable Merkle roots as your community grows in size. You can do any number of things. And what is most interesting to think about in the context of all of this stuff, as always, is your intention. Right? It's not for nothing that I say that there is cultural intent behind this kind of work. And that should indicate quite clearly, I think, that the nature of your intention defines largely the kinds of approach that you take to various different projects. And in this one particularly, like one of the things that I kind of really wanted to make clear, and which I have never seen apart from this gratitude NFT that Angela built for us, is the really creative focus on what it means to use these kinds of cultural objects to create community. Right? It's such an interesting idea if you think about it historically. One of the things that we were reflecting, I think, in the Web3 Communities Guild session last week was that, like traditionally speaking, we've never been forced to think about what community is. A community was just the people that were around you, the people in your village, your extended family, the immediate geographical surrounds. There was never any reason or need to formalize the notion of community, because it was clear it was just everybody who was around me was my community, and there was no sort of pull into digital worlds geographically disparate that got me to question, and therefore brings up the need to formalize this notion of what community is, it means, and how it can be created by people in various different parts of the world. And to me, this kind of work is largely illustrative of the kinds of engineering work that go into creating community. That a lot of it, yes, is this kind of immeasurable and qualitative work to do with interpersonal relationship, to do with creating trust spaces, to do with careful and intentional curation of both content and creators. But an equally important, and if not more pervasive, aspects of this kind of stuff exists at the level of engineering. And it makes me enormously happy that we have a gratitude NFT. I've been speaking about the importance of gratitude for many years now, and how, in fact, in all major wisdom traditions around the world, gratitude is known as the mother of attributes, because gratitude is that thing which gives you perspective and therefore draws you to the very edge of space and time. It draws you to the edge of your own limitations, that when I encounter challenges of any nature or kind, which inevitably come up in community especially, right? Because other people are very, very challenging. They're delightful and miraculous and wonderful, and also deeply frustrating. And when I have gratitude as a foundation for that, it really does draw me to the very edge of my own limitations, and it gives me a wider perspective on what the nature of this cultural moment is about. For Colonel, that's about true and honest expression of who we are and what we value. Because again, it takes us back all the way to module 1. What do we really value? What do you really value? And can we, to at least some extent, use that to generate art that is immutable and that persists across incredibly long time horizons in these shared networks that we use. So we will make all of this code available, and you can play around with it and see what kinds of uses you can put it to. And the only condition, as always, love to be unconditional, but unfortunately we're all human beings and we all have conditions. And the only condition for using this code is that you have to improve it. You can use it, abuse it, take it, share it, do whatever you want with it. The only thing, you have to improve it. So whatever that means to you, please, make sure that's use it with intention, and see where it ends up going. Because I'm just, as I say, incredibly grateful to Angela. Thank you so much for all of your time, all of your preparation. I know that this has been a big thing to prepare for, and so I really appreciate everything that you've done. I'm going to have to create my own whole NFT contract and give you a minter role, and just sort of I'll figure out 1271 maybe, and make you the mentor, be like, permanently that's your role forever in that contract. Which, as you know, is not something that I'm a big fan of, but perhaps in this context it does work, which is hopefully a good example of the importance of context and the nature of our intention. So if anybody has other questions or comments on what we've gone through in the course of this, we'd be willing to field them. Otherwise, Angela, Angela's very busy doing kernel things for me. I just want all of you to know. You can only have a little bit of her time if you. I'm playing. She's actually our CTO. She's, in fact, in the previous block, we made Angela the entire C-suite. She's now CTO, CEO, CMO, COO. And it's just the whole C-suite. So if you have any questions, please direct them to her. I don't know. Amir.
I have one question. Did you say there's like an NFT that's going to be made for Kernel Fellows, or did I misunderstand that?
Yes, there is. What we've showed you now, generally speaking, we don't talk about until the end of the block. Until the end of each block, we're just like, surprise. There's a reason for this gratitude channel. But because we wanted to kind of demonstrate these kinds of distribution strategies in this guild, we talked about it here. So maybe don't tell other people in the block, so that it's like a lovely surprise to them. But the idea here is that you get your unique piece of generative art, which is fairly simple, as you saw all of those kind of different colored circles. But the metadata associated with it is any message in the gratitude channel that has your stack tag in it. So it's like as I say, we've thought quite deeply about like what does it mean to actually have a cultural artifact, right? It's not just some profile picture image. It is a nice start. I have nothing against them, but as Eva by then was kind of talking about with the graph last week as well, like we're only just beginning to realize that like NFTs are the people's APIs, and it's not just NFTs. It's this general sense. That's why I kind of focused quite a lot on ABIs, the application binary interface, and the fact that every single contract has like every function readily accessible to the whole world. It's that like there's so much richness in the metadata that allows us to think really creatively and really broadly about like what cultural artifacts actually are, what kinds of things are valuable, what kinds of meaning we can encode into these shared networks beyond just the fact of a transaction, which itself is an incredibly meaningful thing, but there's so much more that we can do. And so like that's what we were sort of thinking about in this project, is like, okay, wonderful, we can do generative arts, and we can have a nice distribution mechanism, which has been the point of this, but like what we haven't really talked about is the metadata that gets associated with it, which for me personally, as like a text-based person, is the most interesting part. But you can explore that on your own. I mean, at the end of the block, you get one of these.
Well, I'll keep it zipped.
Wonderful, wonderful, wonderful. We're exactly on time, which is so miraculous as to be something that needs to be grabbed immediately. I really do. So I won't waffle anymore. Thank you so very much for sticking with us through all of these 4 sessions. We've covered a lot of ground. I really, really appreciate your presence, your time, your patience, your humor. And of course, we will be around for the rest of the block to finish off the code for this and help you through any of the projects that you're working on, and see where we can get to as a collective, adding to this consciousness which has been growing for all of these years now. Thank you.